Welcome to another physical sciences lesson. Today we're going to look at chemistry, specifically at the rates of chemical reactions. We will be investigating the rate of chemical reactions. Now I want you, while we're going to go through this lesson, I would like you to think about this question. Why do older cars sometimes take a long time to start on a cold morning in winter? I would like you to take some time during this lesson to see if you can answer this question. Now, I'm going to take you through the concept map so that you can see what we plan on doing during this lesson. So, firstly, I would like to go and look at the definition of, I would like to look at the definition of rate of reaction, and then we will link that definition of rate of reaction to the factors affecting the chemical reaction. Now, when we look at rate, as I said, we think in terms of some of our reactions take longer and some of our reactions are very short reactions. And in looking at the factors at a later stage, we will be able to see how we can alter to make a reaction faster or to make the reaction slower. The terminology that's important for this lesson is words like reactant, the substances that we need to start up a chemical reaction, words like product, the substances that are formed, and then the yield, how much of the substances are converted into a new substance. So, as I said, we will look at reactants, products, and yield, and these words or terms will be used a lot. When we look at rate of reaction, I said to you that the rate of reaction is how fast or how slow a reaction is. Now, if we're going to look at just how fast or how slow the reaction is, there's also in the guidelines document, there's a definition that you must study for your exam. And that definition says that the rate of a reaction is the change in the amount of your reactant or product. So you can decide whether you will take the reactant or whether you will take the product, but what's important is you must know that that rate must be per unit time. So whenever you answer anything on rates of reaction, you need to refer to per unit time. In that way, we will be able to see how slowly or how fast a reaction goes. Here I've got a slide on fast reactions. If we look at these three photographs here, we can see combustion, we can see explosion. Now, when we look at fast reactions, as the word says, it's a very quick reaction. It happened over a shorter time. So, fast reactions are normally exothermic reactions, and with exothermic reactions, what's important is the energy that we need, that needs to be absorbed for the bonds to be broken is less than the energy that is released during these reactions. On the next slide, I will just quickly talk about activation energy. Now, for every reaction, there is a specific activation energy at a specific temperature, obviously. So, but the definition for activation energy is one of the terms that we need to understand in order for us to go on with rates of reaction. Right. So your activation energy is your minimum energy that is needed for this reaction to take place. We use the symbol E with a subscript A for activation energy. And as I said, it's the energy that breaks the bonds of the reactants, and that reactants will form new substances or products. So the bonds must first be broken in order for the reaction to proceed. And at the point where the bonds are broken, it means that we have sufficient activation energy for those bonds to be broken. Right. In front of us, we have now 3 pictures of slow reactions. Now, slow reaction will basically mean that the time for this reaction is longer. And what came to mind is the baking of bread, where we use yeast to get the bread ready, but it's not ready immediately. It will take an hour to 2 hours. If you look at rusting, rusting happens over long times where your iron, for instance, are exposed to oxygen and some moist in the air, and that iron will then rust, become brownish on the outside. It's a very slow reaction, but it does happen. When we look at another reaction is, for instance, the fermenting of fruit cells or fruit juices to make wine. When we look at our slower reactions, as per our faster reactions is normally exothermic reactions, where the energy that is released are much higher than the energy absorbed. But when we look at yeasting, for instance, if we look at the energy profile here, we have an endothermic reaction. And again, the energy absorbed for this endothermic reaction is then bigger than the energy that gets released during this reaction when the products are formed. Therefore, it is an endothermic reaction. Right. And we now spoke about the profiles of the energy. We know that energy needed, minimum energy needed to break the bonds, to form new substances. These substances are called products. To break the bonds, we will see color. We will see the reactant get less on a scale. Therefore, we can say on a macroscopic view, we can see certain things. We can observe a color change. We can see that the temperature is changing if we use a thermometer. So on a macroscopic view, we are quickly going to look at the 6 factors that has an effect on the rate of the reaction. These 6 factors, if we look at number one is if I change my temperature. If I look at temperature, I want you to remember that temperature is a measure of the average kinetic energy of a substance. So if a substance has got a high or is exposed to a high energy, it will have a fast reaction. And that fast reaction, we will refer to it as having a high rate. But that fast reaction have got a low time frame or a small time frame that we're talking about. So if your temperature is high, you will have a fast reaction and a high rate. If we look at the opposite, where your temperature is low, you will see that the reaction to form your product will take a much longer time, and we refer to that as being a low rate of reaction. The second one that we're going to look at is the surface area. Now, when we look at surface area, I want you to think in terms of solids. So when we look at solids, when we talk about a large surface area, we talk about small particles. For now, I'm just going to say we will look at powder. So when we have a powdered surface, we will have fast reaction, and we will say it's got a high rate, and this fast reaction will happen in a very short time frame. When we talk about a small surface area, we talk about large particles, and what I can draw here for us is a piece of magnesium ribbon. Now that magnesium ribbon makes up a large surface area. That are the first 2 that we spoke about. A change in temperature can alter the rate of reaction, or it can influence it. And surface area, if it's a small or a larger surface area, that's got an influence on the rate of the reaction. Another factor that I want us to look at is, what does concentration do on a in the macro view the macro view, we know that concentration, according to our chemistry formulas learned to date, is the number of moles per volume. So if there's a high concentration, because concentration is directly proportional to the number of moles, it means that a high concentration will have a high number of moles. That will have a fast reaction, high rate, meaning in a small time. Low concentration means there will be a low number of moles, and it will go for a slow reaction, and a slow reaction happens in a longer time. The fourth factor that we're going to talk about today is pressure. But when we look at pressure where we use gases only. And the gas must be part of your reactant, not necessarily part of your product. So when we have a high pressure, we have a fast reaction, a high rate of reaction, and at a low pressure, we have a slow reaction and a low rate, meaning longer time. Then catalyst. When we get to catalyst, firstly, I would like to say that a catalyst is a substance that can have a positive or a negative influence. It can make a reaction faster or it can make a reaction slower. So just to look at catalyst, catalyst is a substance that changes the activation energy, and when this activation energy is changed, it is not used up during the process. So it does not take part in the reaction. When we look at positive catalyst, a catalyst that will speed up, it makes the reaction faster, but it makes the reaction faster by lowering the activation energy. So it makes the activation energy lower, makes the reaction faster, and it is then a high rate. Now, I just want to show you the energy profile where we put in a catalyst to show you what we mean by saying decreasing or lowering the activation energy. In front of us here, we have an exothermic reaction, and for this exothermic reaction, we can see that our delta H is negative. So what I want us to see is, under normal circumstances, we would have needed that activation energy for this reaction to take place. But when we have a positive catalyst, we now lower the energy to a point where we only need that amount. So if I can draw it like that, you will see it looks as if this reaction can take place so much faster. Negative catalyst does the opposite, meaning it increases the activation energy, and when it does that, it actually slows down the reaction, slows down the rate of the reaction. Then the very last factor that I want to talk about is, and this factor we don't talk about a lot, but it is a factor that needs to be taken in consideration, and that is the nature or the type of reactants that we use. Now, some of our group 1 and our group 17 elements, when they react, they are very reactive. Not some of them, all of them are very reactive elements. They make for a fast reaction, high rate reactions. But if you look at your inert elements like nitrogen, gold, platinum, they don't really want to react. So when they in a reaction, they have slow reactions, low rate, meaning it takes long times for these reactions to take place. And this brings us to our first break. See you just now. Welcome back from the break. We will continue with rates of reactions. If we can just go back to our concept map to see where we should go on. We first did the definition of rates of reaction, and then we looked at the factors affecting the rate of reaction. We spoke about the 6 factors that affect the rate of reaction, and for now I would like us to go look at the ways to measure rate, and then with that ways to measure rate experimentally, I will also show some graphs to just sensitize us as to what will follow afterwards. When we look at ways to measure the rate of reaction, firstly, I said to you in the previous session that there are 6 different factors that affect the rate of the reaction. These 6 factors can be altered, and that will then now change the time that the reaction takes place. But when we do this experimentally, there are ways to do it to make sure that we have more or less an accurate experimental setup. With doing it experimentally, we obviously need the right apparatus for us to be able to measure the rate of the reaction. In the first case, I would like us to measure a decrease in the mass, and a decrease in the mass means that the mass is getting less over time. But that is, what mass are we talking about there? We're talking about the reactants mass, and then we obviously have to do it, the measurement over regular time intervals. An example that I would like us to discuss here is when we take zinc as a solid and mix it with hydrochloric acid in a conical flask to get to see how the mass decreases over time. Now, just before we're going to talk about how the mass decreases over time, it's sometimes important for you to know the names of the apparatus, for in case they ask some of these in the exam. Sometimes they can ask us, how will you set up such an experiment for you to measure the decrease in mass? In front of us, we will now have a conical flask where we will have our reactants in. And in this case, we have zinc and hydrochloric acid. And we can see that we will use a ball of cotton wool there, but the cotton wool will not be in the way for the escape of the gas. It will still allow the gas to escape. What you also need is a balance so that you can see the mass. And obviously, if you're going to use a timer, you can see for regular intervals what happens to the mass over that intervals. When we measure the decrease in mass over that regular intervals, we can now go back and mathematically use the equation where we say rate is equal to negative change in mass over time, and that negative change in mass over time will actually now be the gradient of our mass over time for this specific reaction. Now, just before we get there, that negative in front where we speak about rate is equal to negative change in mass over delta T. That negative does not mean that the mass is negative. It just means that because the mass is decreasing over time, we know that it's a negative gradient that we will have there. Back to the graph, we will see we obviously have a mass because our reactants will have a mass. And that reactants is there now in that conical flask that we just spoke about. At the beginning, we will see that we have a steeper slope there, and the slope becomes less steep to a point where it is parallel to the time axis. Now, when it is parallel to the time axis, that is the time where your rate is actually 0. But before I get there, let me start at the beginning. We start with some mass. After a time, the mass is less. After a time, the mass is less. Up to a point, like I said, that segment there, the mass will then be staying the same, meaning that the rate of the mass there will be 0. if we look at this, like I said, initially there is a lot of reactant in the vessel, and you have a fast reaction. The reason for a fast reaction is because we have a lot of reactant that can react to, in a fast manner, form our product. As the reaction go on, you will see that the curve becomes less steep to a point where it flattens off, where it actually stopped. Now, what will let the reaction stop? At least one of the reactants are used up. And how will we know that? As I said, if you read it from your graph, you will see on your mass of reactants axis that you have the same mass for that period of time. And as I said, the expression mathematically will be rate is equal to minus mass over delta T. Another way, I would say, the second way to measure is to go and do the same experiment, but this time we don't look at the decrease. We this time allow the gas to be caught up somewhere. So what we can do is we change the experimental setup, and we want to go look at the increase of the volume of the gas for the second one. So what is the gas that we're going to catch up here? It's going to be hydrogen gas, and this hydrogen gas, with the proceeding of the experiment, it should be released, and it will be released into a syringe, and that syringe will then show how it fills up, and we will then read from the syringe the volume of the gas that's there at that specific time. Now, when we do the volume of a gas, we expect of the volume of the gas that we catch up to become more over time while the reaction is going on. But obviously, there will be some time that your volume in the syringe will stay at the same reading. That means one of our reactants is used up. So back to the mathematics, to work out the increase in volume, we can use the rate as delta V over delta T, where this is your volume, and it can be in centimeters cubed over the time. That can be in minutes, seconds, and the rate is then centimeters cubed per second. Then a typical graph will look like this, where we have a steeper gradient, less steep, having parallel to the time axis, showing that the volume remains the same for that period of time, and the rate of the reaction is then the gradient that we're looking at. Right. So again, beginning, fast reaction, slower, stop of the reaction, flat curve, reaction is finished. Right. The very last one, the third one that I want to look at, is the one that we can do as a practical, a formal practical in grade 12, where we measure the color change, how long it will take for the color to change. And we use here sodium thiosulfate and hydrochloric acid in a conical flask on a white tile with a black X at the bottom. We look at from the top, then we can see as soon as the sulfur precipitates, it will go to the bottom. It will make the color of our solution milky to something that we cannot see through anymore. On that time, we take the time and we link the time to concentration. So we will, for instance, use different concentrations of hydrochloric acid when we use it with the sodium thiosulfate. And now I think we're all ready for an ad break. Let's go for it. Welcome back to the physical sciences section, and we carry on with rates of reaction. When we look at what we've dealt with previously, we looked at the macroscopic view, meaning what we can observe, what we can see, the changes in temperatures, the changes in color. We looked at the macroscopic view, and we linked that to the factors affecting the rate of a chemical reaction. We then also looked at the ways, macroscopically, the ways that we use experimentally to work out the rate of reactions. We also touched on the different graphs that we get when we do that. What we are going to do now is we are going to look at the submicro view or the microscopic view where we cannot see it, but what actually happens on a particle level. So, as I said, macroscopic view is what we can observe, what we can see during a reaction. We can see if we use a thermometer, there's a temperature change. We can see that there's a color change, like with the sulfur, and we can see or feel if something is getting hotter or colder. But on a submicro view or a microscopic view, we're actually looking at things that we cannot see, but it happens in the reaction, even though we cannot see it. Another term that's important is the collision view and the collision theory, and I will explain to you what the collision theory is as we proceed. So if we look at the submicro view of a reaction, let's say this is my representation for particle A, which is my reactant, and particle A converts and become a product, which is now particle B. And we use red for the reactant and blue for the product so that we can see what happens to the red particle during a reaction and where the blue particle comes into play and what happens to the blue particle as the reaction goes on. In front of us we have a closed vessel, meaning no gases can escape from here. And let's say we look at the reaction of A that converts into the product B, which is the blue product. So at the beginning, when our reaction starts, we can see in our closed vessel, we only have reactant, only red little particles. As we proceed here, we have more blues, and let's say at a time of 20 seconds, we have blue and red in your flask that's actually closed. And at this point, we will see that now we only, from the 1 mole of A, we only have 0.6 mole of A left. But in the meantime, some of that A converted into B. That's why we see the blue particles in between. And at a later stage, 40 seconds, regular time intervals, we can see that there's even a further change where I have 0.4 mole of A and 0.6 mole of B. At this stage, it might be the end of the reaction, but we can see at the end there is now more products than reactants. As I said, when we look at the microscopic view, what's happening at a level where we cannot see it with the naked eye? We call that the microscopic or the submicro view of this reaction. When we talk about collision theory, we know that all matter is made of particles, and that particles is in constant motion. That motion depends on the temperature. We know that if it's a high temperature, we've learned before, we know that the motion will be fast. At a low temperature, we know that the motion will be a lot longer. You need to have a collision between two particles for a reaction to happen. Now, at this point, I just want to say, if we look at collision, we can say it's a bumping of our particles, or we can say the particles hit each other, or the particles hit against the inside of your vessel. But if there's no bumping, or no hitting, or no collision, there will be no reaction taking place. The example that we have in front of us, we have hydrogen gas where we see the bonds that reacts with oxygen gas. If this hydrogen and oxygen do not get in contact with each other, if they do not collide, nothing will happen, no water will form. But as soon as this hydrogen and the oxygen is placed in the same container, they will start to hit each other, they will collide, and they will then possibly go over into forming water, which is the product. But there is a temporary, unstable uphill, as we call it, period in this chemical reaction, and we call that the activated complex. It's got high energy at this complex. We call it energy hill because there's so much energy. So during that time, there's a bumping, but if that bumping or that collision is not a correct collision, we see that it will not form water. When we do have the collision taking place the right way, in the correct way that we need it to take place, we will see that after being in that unstable state, it will form the water molecules. So this brings us to the collision theory. Remember, all matter is made of particles, particles that moves, and that movement depend on the temperature. So the kinetic energy of the particles before the collision must be right. This is important. If that kinetic energy is a bit too high, if we have two atoms, we will see that that two atoms, the positive force from the nucleus, will start to repel each other. If that kinetic energy is too low, the electron clouds around the nucleus will start to repel each other. So too high, the positive and the positive will repel each other. Too low, the negative and the negative will repel each other. But if that happens, we say that the collision is unsuccessful. That collision that's unsuccessful will not ever result in a product. But when we have the kinetic energy of the particles, if it's just right, it will break the bonds between the reactants, and it will form new bonds for the products. And when that happens, we say that that is an effective collision. An effective collision will go over into forming product. So the rate of reaction is then determined by the number of effective collisions per unit time. You must bring in the per unit time. So for the last, I just want to say, for a reaction to be successful, for a reaction to produce product at the end, we need to look at the requirements. There must be a high number of collisions that take place. And that collisions, that particles must have a kinetic energy that is bigger or equal to the activation energy. If that happens, there might be product, but there's something else that we need. We need the correct orientation. In other words, if hydrogen and oxygen is now overlapping and your unpaired electrons overlap with their orbitals, we have just the correct orientation for it to happen. And that will lead to an effective collision. Now it's time for a break. Go and get revived and refreshed. Welcome back from the break. We're getting back to the concept map, back to rates of reaction. In the previous sessions, we looked at the definition and the factors on a macroscopic view. We looked at the ways to measure rate. We also looked at graphs. And now I would like to go and look at the factors, but now I will link the factors to the collision theory on a microscopic view. So I just want to remind you that microscopic view actually means what we cannot see, but what we know, according to the collision theory, is happening microscopically. So we spoke about the factors affecting the rate of the reaction, and in an earlier session we said that temperature, surface area is specifically the surface area of solids, the concentration of solutions, meaning in solution where we use AQ, the pressure when we have gases. When we add a catalyst, we're specifically going to talk about a positive catalyst because that's what we do at school level. And then we should remember that the factors affecting the rate is also the nature of our substances, where we, for instance, said if you have an inert substance like nitrogen, gold, or platinum, they don't react very frequently. They don't really want to react. But if you look at your group 1 and your group 17 elements, they are highly reactive. And if you look at that nature, it will normally have a higher rate of reaction. The first question that I would like us to answer is, why does an increase in temperature, meaning when the temperature is hotter, why does it result in an increased rate of reaction? Now, you should remember that we said earlier that according to the collision theory, all particles are constantly in motion, and how fast or how slow they move actually is a factor of the temperature. Now, if the temperature is increased, we need to know that the temperature is a measure of the kinetic energy of a substance. And remember, the kinetic energy, where we know that Ek is equal to half mv squared. So when we talk about kinetic energy, we should then think about the speed of our particles. When we have hotter temperature or higher temperatures, we will have the particles will move at a higher speed because of the average higher kinetic energy that the particles will have. So the higher the temperature, the faster the motion of our particles. The particles will collide or bump or hit each other more frequently. So we will have more collisions per unit time. Remember, this per unit time is all to do with the rate of a reaction. And if we have more particles per unit time, we will most likely have more effective particles, more effective collisions per unit time, and then that leads to a higher rate of reaction, meaning a rate that takes a reaction that is faster. I just want to remind you again, when we talk about effective collisions, we're talking about collision where the kinetic energy is bigger than or equal to the activation energy. That's firstly. And secondly, there must be a correct orientation, meaning there must be an overlap in the unpaired electrons orbitals. The next factor that I would like us to look at is, or the next question that we have coming up is, why does an increase in surface area? Now, when we talk about surface area, I want us to know that surface area plays with the brain a little bit. So when we talk about a big surface area, we always think about something big. But the surface area that we refer to is actually the contact area of that solid, meaning how much contact area is in that solid that can collide or hit against each other or bump against each other. So the finer your solid, meaning if you have powder particles, there will be more space for the collisions to happen, and it will lead to an increased rate of reaction. So if we look at what we have in front of us here, we actually have 1, 2, 3 from the front, 4 from the bottom, 5 at the back on this side, and from the back we have here 6 sides that is exposed to this reaction. But when we take that same piece that same lump of your reactant and you make it finer, you make it into powder form. Let's say every one of the small squares is a powder, a piece of powder granule. Then we can say if each one of them have 6 sides for collision or possible contact area, and we have 9 of them, we can see for the powder, we actually have 56 contact areas as opposed to the 6. That is why we say powder form is a higher or a bigger surface area as opposed to a lump. But you must remember, for a fair experiment, you must have the same mass of your reactant. When we have surface area that's bigger, if we look at this surface area there, it's a smaller surface area than the one next door. So if we have the collisions that take place, it takes place on the surface area, and like I said, we say it is the contact area. The larger that contact area, meaning the more possibility of contact, the more collisions will happen per unit time. And what do we know? When there's more collisions per unit time, we know there will be a likelihood of more effective collisions per unit time. And if we have more effective collisions per unit time, we actually have a faster rate of reaction. And then I know you can remember this, but I just want to remind you again. An effective collision is a collision where the kinetic energy is bigger than or equal to the activation energy. That's the first requirement. But there's a second requirement, and I know you know what the second requirement is. Yes, the second requirement is there must be correct orientation. When both these are met and we have many collisions happening, we will have a higher or a faster rate of reaction. And that brings us to the next question. How will an increase in concentration, why does that increase in concentration result in an increase of the rate of the reaction? Again, when we look at concentration, we should think of the following. Concentration is equal to the number of moles over a specific or a given volume. So if we can look at that, as soon as I increase my surface area, my concentration, and I keep my volume constant, then it actually means that my number of moles will also increase. I can actually say that the number of moles is directly proportional to the concentration. Higher concentration, higher number of moles. So if I have a higher number of moles for the same volume, you can think, in the same small space, there's now more particles, and these particles will now collide more often. So when we look at the collision theory, we will now know that the increase in concentration leads or comes from an increase of the number of moles. And back to the C is equal to N over V, we can say the C, is directly proportional to the N, but that is only the case when my volume is constant. So according to the collision theory, we need to explain it in terms of the particle motion and the collisions, and we need to talk about the effective collisions per unit time. So an increase in concentration of the reactant will mean there is now more reactant particles per volume. So there will now be more collisions, so there will be more bumping per unit time. And if there's more bumping per unit time, there's a possibility of more effective collisions per unit time. And when we have more effective collisions per unit time, it basically means that we have a higher rate of reaction. The reaction is now faster. That brings us to our next factor. Our next factor is only applicable to gases. So whenever you see pressure, think gases. So when we talk about pressure, we can look at the next question where we ask, why does an increase in pressure lead to an increased rate of reaction? How can that happen? Right, so when we talk about an increase in pressure, the first thing that we need to remember, and this comes from earlier knowledge, that pressure is actually the force per area, and we will say it's the force per unit area. And according to Boyle's law, we've also heard and learned that pressure is inversely proportional to the volume, or the volume is inversely proportional to the pressure. So, firstly, if I say that the volume and the pressure is inversely proportional, that will basically mean if I decrease my volume, so if I have that volume with my little particles in, and I decrease my volume, let's say to half of the previous size, and I still have the same number of particles. Remember, your number of particles must stay the same. Then it basically means in a bigger volume, I have less pressure because there's less collision, and in a smaller volume, I have more pressure. So I can say, when we look at pressure in gases, we need to always know that it is connected to the volume. A decrease in volume leads to an increase in pressure, and an increase in volume leads to a decrease in pressure. Here I show you that we've got the same number of moles. Remember, the number of moles must remain the same so that we can say, in a fair experiment, when I decrease the volume, my pressure will increase. Right, so just to explain, why does an increase in pressure lead to an increase in reaction rate? According to the collision theory, we can now say that a decrease in volume leads to an increase in pressure because there's now more particles in that small space. So we have more collisions per unit time, and if there's more collisions per unit time, it basically means there's a likelihood of more effective collisions per unit time, which leads to a faster rate of reaction. So, all well, we're going on. We're going to the next one. We will go look at the next one. Why does an addition of a positive catalyst result in an increased rate of reaction? Now, we spoke about a positive catalyst before. We said it lowers the activation energy. If we can just look at an energy profile, if that is my activation energy, when I have a positive catalyst, I will have an alternative path, a path that leads to my product faster. Remember, it's the same amount of product, we just read product stage faster. So, provides an alternative path after lowering the activation energy. You need to know it's not used up at all in the reaction, or not used at all, and the same amount of product is formed. So when we look at the effect of the collision theory, we now know that if it's a positive catalyst, there will now be a lower activation energy. There will be more collisions per unit time. There will be more effective collisions per unit time. That leads to a faster rate of reaction. And again, only the time frame changes, but not the product. Product remains the same. Then we spoke about the nature of the products, in what group they are, the reactivity, that's important. In closing, I would like to remind you of the following. Reactions happen at different rates. Reactions can be fast or slow. It all depends on what we're reacting. There are different factors that affect the rate of a reaction. And we said, and we spoke about 6 of these factors. We spoke about macroscopically, as well as microscopically how they affect the reaction. These factors can be explained by looking at the submicro view of a reaction, and when we look at the submicro view of the reaction, we spoke about the collision theory. So for now, that's me. Thank you.